Starship isn't just the largest rocket ever built, it's also one of the most complex pieces of plumbing humanity has ever created. And at the heart of this monster, two gigantic cryogenic propellant tanks, one for liquid methane and one for liquid oxygen, working together in perfect harmony. But why two different fuels? Why not just one? And how do these tanks manage to feed 33 engines at liftoff and then switch to a completely different mode for spaceflight and landing? Stick around, because by the end of this video, you'll see how the dual tank system gives Starship its insane power, efficiency, and even its reusability edge, and why SpaceX chose methane over the traditional RP-1 kerosene. Hey everyone, welcome back to the channel. If you're obsessed with rockets, deep space, and the future of human spaceflight, you're in the right place. Make sure to hit that like button, subscribe to our rocketry channel, and follow us on Facebook for daily space updates. Starship is a two-stage, fully reusable launch vehicle, the Super Heavy booster and the Starship upper stage. Together, they stand at nearly 121 meters tall, making it taller than Saturn V and significantly more massive. But what makes it work? What makes it fly is propellant, and specifically, liquid methane and liquid oxygen. Every rocket engine needs two things: a fuel, something that burns, and an oxidizer, something that helps the fuel burn, especially in the vacuum of space where there's no oxygen. In Starship's case, the fuel is methane, and the oxidizer is liquid oxygen. That's why we call them dual propellant tanks. The methane tank sits on top, and the oxygen tank sits below it, separated by a common dome that saves weight and simplifies design. This setup means one tank ends where the other begins, and they share a single structure in the middle instead of two separate domes. Pretty efficient, right? But this arrangement wasn't always the plan. Early Starship prototypes, like the Starhopper, were purely methane test beds. The full dual setup came later, and for good reason. So why did SpaceX pick methane as the fuel for Starship instead of RP-1 kerosene like Falcon 9 or liquid hydrogen like the Space Shuttle? To answer that, you need to think long-term, not just about launch day, but about Mars. Methane has three key advantages. First, it's clean burning. Unlike RP-1, methane doesn't leave sticky carbon residue inside the engines. This means SpaceX can reuse Raptor engines multiple times without tearing them apart for cleaning. Second, it's easy to make on Mars. Through the Sabatier process, carbon dioxide from the Martian atmosphere can react with hydrogen, which can be extracted from Martian ice to make methane and water. That means future missions can refuel on Mars before coming back to Earth. And third, it's dense and storable. Methane is denser than hydrogen, so you need smaller tanks. It also doesn't need to be kept as cold as hydrogen, reducing insulation needs. So methane gives you efficiency, reusability, and the key to interplanetary logistics, all in one molecule. Now let's talk about the other half of this equation, oxygen. Oxygen might sound boring, it's everywhere, right? But in rocket terms, it's pure magic. Methane can't burn by itself, it needs oxygen. And since there's no atmosphere in space, rockets have to carry their own oxidizer. Liquid oxygen, or LOX, is stored at cryogenic temperatures around -183 degrees Celsius to keep it dense and liquid. It makes up about 78% of Starship's total propellant mass. Yep, most of the tank space is actually oxygen. That's why Starship's lower section, the big tank, is the LOX tank. The methane tank, which holds the fuel, sits above it. But these aren't just two simple tanks stacked together. They're part of a highly integrated system that must maintain perfect pressure balance, temperature, and flow rate during flight. Between the two tanks lies one of Starship's most underrated features, the common dome. Imagine if you had two separate tanks, each with their own top and bottom domes. You'd have double the material, double the welds, and more weight. Instead, SpaceX merged the bottom of the methane tank and the top of the oxygen tank into a single shared dome. This saves tons of mass and simplifies the structure, but it also introduces complexity, because one side is holding super cold methane at -161 degrees, and the other side is holding oxygen at -183.
That's a 20-degree temperature difference across a single piece of stainless steel. To make that work, SpaceX uses 304L stainless steel, which remains tough and flexible at cryogenic temperatures. So, the next time you see a Starship tank section being welded at Starbase, remember, that shiny dome isn't just a cap, it's the heart that separates two oceans of cryogenic propellant. Both the methane and oxygen tanks are connected to complex feed lines that run down through the rocket's internal plumbing into the cluster of 33 Raptor engines at the base. But here's the twist. During different phases of flight, Starship doesn't always use the same tanks the same way. At liftoff, the main LOX and methane tanks feed the booster's engines at incredible rates. More than 3,400 tons of propellant are consumed in just over 2 minutes. Once the Super Heavy booster separates, the Starship upper stage takes over. It has its own smaller methane and oxygen tanks, with the same dual arrangement. But even that's not the end of the story, because during landing, things change dramatically. You've probably heard about Starship's header tanks, the smaller tanks used during landing. These are mini versions of the main tanks, located near the nose for methane and near the base for oxygen. Why? Because as Starship performs its famous belly flop maneuver, the main tank's propellant sloshes around too much for a stable flow. So instead, Starship switches to the header tanks, which stay pressurized and stable even while the vehicle flips vertically for landing. These tanks feed the Raptor landing engines, giving Starship those iconic controlled burns just seconds before touchdown.
It's a brilliant design, one that keeps the main tanks simple and massive while using smaller, well-placed header tanks for precision operations. Cryogenic propellants are incredibly efficient, but they're also a nightmare to store. Methane starts boiling off at around -161 Celsius, and oxygen at -183. That means any heat that seeps into the tanks can cause pressure spikes or fuel loss. To combat that, SpaceX uses active autogenous pressurization. Instead of using helium like other rockets, Starship uses its own fuel and oxidizer gases to pressurize the tanks. Here's how it works. A small amount of methane and oxygen is heated and turned into gas. These gases are then piped back into their respective tanks to maintain pressure as the liquid propellants are drained. This reduces the need for external pressurization systems and eliminates the complexity of storing helium at high pressures. It's another step toward full reusability and self-sufficiency. Rocket engines need a precise ratio of fuel to oxidizer to work efficiently. For the Raptor engine, that's about 3.6 parts oxygen for every 1 part methane by mass. Too much oxygen and you burn too hot. Too little and you lose efficiency. SpaceX carefully balances this mixture ratio to optimize both thrust and specific impulse, basically how efficiently the engine uses fuel. And since Starship's tanks hold thousands of tons of propellant, even a 1% shift in ratio could mean a massive performance difference or catastrophic engine issues. The tanks and feed systems are therefore meticulously calibrated, using sensors, valves, and computer-controlled flow management.
You might still be wondering, why not combine both propellants into one hybrid tank? Simple. Physics won't allow it. Methane and oxygen must be kept completely separate because they're reactive. If you mix them, you get combustion, and not the kind you want inside a rocket body. Keeping them apart also allows SpaceX to optimize temperature control, pressure management, and plumbing layout for each propellant individually. The oxygen tank is larger and heavier, sitting lower for better center of gravity during ascent. The methane tank sits above, feeding from the top and venting through its own lines. Together, they create a beautifully balanced system, one that handles the massive flow of cryogenic fluids with surgical precision. Reusability isn't just about landing the rocket, it's about doing it again quickly. With Falcon 9's RP-1 kerosene engines, carbon residue built up inside the engines after every flight. That meant long, expensive cleaning and inspection processes. Starship's methane burns clean, leaving almost no soot behind. That means the tanks, feed lines, and engines can be turned around much faster. Plus, the autogenous pressurization system means fewer moving parts and no disposable helium bottles. Every component is designed to be refueled, repressurized, and relaunched. In other words, the dual-tank system isn't just about flight, it's about reuse. If you followed Starship testing at Starbase, you've probably seen dozens of tank tests. Cryo tests, burst tests, pressure tests. Those aren't just structural experiments, they're direct rehearsals for how the dual tanks behave under extreme cryogenic stress. When you cool a 9-meter wide stainless steel tank from room temperature to minus 180, it shrinks by several centimeters. Weld seams tighten, domes flex, and pressure must remain perfectly controlled. Some early prototypes, like SN1 and SN3, collapsed during testing. But each failure taught SpaceX how to build better tanks, with stronger welds, stiffer bulkheads, and improved common dome design.
So the next time you watch a Starship test flight and see that massive plume of fire, remember, it all starts deep inside those two cryogenic tanks, where methane and oxygen dance in perfect balance. That's what makes Starship not just another rocket, but a stepping stone to becoming a multi-planetary civilization. If you enjoyed this deep dive into Starship's dual propellant tanks, make sure to hit that like button, subscribe to our rocketry channel for more deep space breakdowns, and follow us on Facebook for exclusive updates from the world of spaceflight. Because we're just getting started, and the next big leap could be closer than you think. Stay curious, stay inspired, and keep looking up.